we're going to start learning about reinforced concrete design. And we're going to spend the bulk of the semester on Flexural. And first we're going to talk about the theory behind all of it, and then determining strength, and then doing design, which hopefully you'll understand that in a minute. So all of this will be our assumptions and simplifications. There's going to be some free body diagrams, throwback to mechanics of materials, and all that good stuff. We're going to, by the end of this, we should be able to determine the design flexural capacity. We're not going to design stuff, but we're going to know the capacity of singly reinforced, doubly reinforced, and flanged sections, which you will figure out what all that means in the coming weeks. So, analysis versus design. For now, we're sticking with analysis in terms of calculating the strength of a given section. That's what we're going to mean by analysis. And there is only one answer. One right answer. When we're talking about design in this class, I'm talking about choosing a section or a cross section to support given loads. And in that terms, there are multiple right answers. So analysis is when we're given something and we have to calculate its strength. Design is when we have to actually choose the section to make sure that it supports a given load. And there's multiple right answers so long as the answer meets the criteria that you give it. As a reminder, the required strength is MU. That's our factored loads. That's our factored moment, because we're talking about flexure, so we're talking about moment. And that has to be less than or equal to our design strength. This is our phi factor times our nominal moment strength. MU is our factored moment due to loads, right? Due to our dead load, live load, whatever other loads we have. And our phi mn is our design strength, right? which is our phi factor times our nominal moment capacity, moment strength or capacity. And our phi factor is going to vary depending on whether the cross section is tension controlled or compression controlled. Whereas typically in steel, phi would always be the same. If you're talking about compression or tension or something, our phi factor is actually going to vary the whole for flexure, although you want it to be a certain value. So here we have a moment diagram for this supported beam, right? Continuously supported beam, or not continuously supported, but continuous beam over 4 supports, subjected to some type of distributed load. And as a result, we get this moment diagram. This moment diagram is actually upside down compared to our what we have talked about before, right? We have positive moment on the bottom. Positive meaning it makes a happy little face, right? That's probably my display shape, something like that. Or maybe not. But, and then we'll have our negative moment at the supports in the middle. And we have our reinforcement. We're going to have 2 different spots for reinforcement. In the bottom, let's make that a little bit closer to the bottom. All right, in the bottom and in the top. So we can have reinforcement in the bottom and the top. And if we're talking about like this section right here, then we're going to have tension on the bottom and compression on the top. That's the definition of positive bending. Tension on the bottom, compression on the top. And if we look at, say right here, now we're in negative bending. So we have tension on the top and compression on the bottom. Reinforcement is primarily for tension because concrete is terrible in concrete is good in compression, but bad in tension, right? If you remember from the stress strain curve. So that is the purpose of the reinforcement, steel reinforcement. The steel reinforcement is going to carry the tension loads. So in this section of higher negative moment, the steel up at the top is going to be carrying that tension force, and in this positive bending, the steel on the bottom is going to be carrying the tension of the positive bending. Typically, we are going to assume positive bending. So we're going to be talking about steel in the bottom of the cross section. So let's look at, we're going to talk about the symbols that we use. Let's first look at, I'm going to, for both of these, red is tension, and blue is compression. So if I talk about positive bending moment, remember which side was tension, top or bottom? Top or bottom was tension. It's the bottom, right? So let's say this part is in tension and the top is in compression. So this steel right here, those are my three, I have 3 steel reinforcement rods. This is referred to as AS. AS is my area of tensile reinforcement. So whatever size those 3 rods are, I'm going to find their cross-sectional area, add it together. That's my AS. AS is an area. That would be in inches squared. Up at the top, this is my AS prime. When we're talking about the compression side of things, we add a prime to it. So that is my area of compression reinforcement. Right? I take those 2. The area of those the cross-sectional area of those two rods, add it together, and I come up with my area of compressive reinforcement. There are some distances that I need to know. If I start, I always going to start from the top. Well, that's not true. I'm going to start from the compression side. If I can draw a straight line. The distance to the centroid of my compression steel is D prime, and from the centroid, the distance from the extreme compression fibers to the centroid of my tensile steel is D. So regular D is distance from my extreme compression fibers to the centroid of AS, my tensile reinforcement, right, that's in inches, D, and then my D prime is the distance from the extreme compression fibers to the centroid of my compressive steel, AS prime. That's also going to be in inches. The other dimension that we care about is the width, which is B. So we got B, which is the width of my cross section, which is in if I look at the negative moment cross section, everything is the same, just upside down, right? This part is in tension in the top, compression in the bottom. My area of tensile steel, here I have 6 bars. My area of compression steel, right, make sure I said tensile steel. Tensile steel has 6 bars. I have 3 bars in my compression, in the compression side. If I'm going from the extreme compression fiber to the centroid of my compressive steel, I got a D prime. And then here the centroid, you see the centroid is going to go through the group of 6. That's the distance from the extreme compression fiber to the centroid of my tensile steel. I still have the cross-sectional width of B. So it's the same thing as the positive moment, it's just upside down. But these are the symbols that you're going to be very familiar with by the end of the class. AS, AS prime, D, D prime, and B. So now I want you all to channel your inner structural analysis, and I want you to draw the moment diagram for the simply supported beam subjected to a concentrated load in the middle. I'm going to give you a couple minutes to do that. Okay, it's been a couple minutes. I hope you figured it out. It's really easy, right? If you got air P, simply supported P over 2. P over 2, right? It's all symmetric. You should have 0 moments at the middle. Or, sorry, 0 moment at the end. At the middle should be PL over 4, right? Because P over 2 times L over 2, PL over 4. So we're gonna use this moment function, but I figured we had a little quickie review, right? So we have our PL over, where's the middle? Right there. Something like that. And I'm gonna draw a little, I'm gonna cut the beam right here, right? Got my P over 2, got a P right here. So I'm just cutting it not at the middle, is what I'm doing. And if I look at my internal forces, got a shear force, which would be equal to P over 2, and a moment. Which would be equal to P over 2 times whatever that length is where I cut it. So those are my internal shear and moment. If I further break down that shear, that moment into, right, I have my shear, I'm going to break down that moment into tension and, let's keep it red, compression, right? So we talked about how that moment is distributed into compression and tension, about the centroid of the cross section. This should be review from mechanics of materials and structural analysis. Now I'm just going to look at that one. I'm just going to look at just going to look at this side over here, right? On the next slide. So let's see, I've got my, I'm going to draw all my forces again, right? I have my P over 2, my tensile force, compressive force, and a shear acting on that cross section. I'm gonna make that in red. The distance between these, the compression and the tension force, is some distance J D. Length of this section of beam is X. Let's do some checking of my free body. This is my free body diagram. I'm going to make sure it's all in equilibrium. So if I do the sum of the forces in the x direction equals 0, I get the 2 in the x direction is C equals T, right? I get my compressive force equal to my tension force. If I do the sum of the forces in the y direction, I get my shear is equal to that P over 2, but we're not going to care about that right now. I'm going to take a moment, about a point A, which coincides with the compressive force. Some of the moments about A, counterclockwise positive. I've got T times JD. Right, if I take the moment about A, I don't have to care about C because it coincides with the point A. I don't have to worry about V because it coincides with point A. It would have a 0 moment arm. So I've got T, my tensile force, times that lever arm, JD, acting counterclockwise. Right, you go down to the right, that's counterclockwise. And then I have P over 2 acting like that, so negative because it's clockwise, minus P over 2 times X equals 0. If I choose a point B coinciding with my tensile force, some of the moments about B is 0. I don't have to worry about T because it's coincidental with point B. Same thing with the shear force V. So I have C times JD acting counterclockwise, so it's positive. And then I have, again, my P over 2 acting, right, clockwise. The force is P over 2, the moment arm is X. say I put these two together. T times j over 2 minus p over 2x, c times jd minus p over 2 times x. Actually, I'm going to subtract one of them, right? If I subtract it, I get t times jd minus c times jd equals 0. Negative p over 2 times x plus p over 2 times x. Can factor out that jd, and so again I get c equals t, which is similar to what I got up here, right? We're just proving our compressive force must equal our tensile force for the cross section to be in equilibrium, for the beam itself to be in equilibrium. Now I'm going to talk about some elastic beam theory. We did this a little bit in, you should have done this a little bit in structural analysis. So we're going to talk about the distribution of the stresses within the cross section. So here is my, right, I'm going to look at this cross section of my beam. Up here, it has a height of h, subjected to a moment, a positive bending moment. And this dashed line represents the centroid of the cross section, and I'm going to assume that above it is plus y, which is the distance from the centroid of the cross section. And my assumptions are a homogeneous uncracked homogeneous rectangular beam cross section, I guess. Where my stress, my maximum tensile stress is equal to my maximum compressive stress. If if I draw the stress profile, it would be like that, where the top is in compression, and the maximum is your compressive stress, maximum, and the lower half below the centroid is all in tension. Right. That's our maximum tensile stress. We can calculate those two quantities, the maximum tensile and compression stress, by using the equation my over I, or mc over I, c being, like, if it's the maximum, right, it would be c. You guys may be familiar with that nomenclature. The value along the height is my over I. The maximum is mc over I. And similarly on the bottom. Now I'm going to take my stress profile here, draw it again. And I'm going to resolve that triangular stress distribution into a single force C at the top, right? It'd be 1/2 the height times 1/2 y over 2, or h over 2 times whatever my maximum stress is. And I'm going to find the resultant of the tension as well. I'm going to draw it out here though, but the resultant of the tensile stress, the distance between them, is JD. That's that lever arm. And right now we know, let's see, this would be 1/3 of h over 2. So 1 over 3 times h over 2. The height is the cross section that is in compression is h over 2, because that's my cross section height. And I know that that distance is 1/3 of it. So this distance would be 2/3 times h over 2. Similarly, on the other side, because it's symmetric and homogeneous, this would be h over 2, 2/3. So that distance, JD, is equal to 2/3 h over 2 times 2. So 2/3 times h wanted to know what my capacity or what my moment was, I could shift that equation up here from my over I equals stress to m equals stress times I over y. And if I wanted to know my maximum volume, my maximum moment would be my maximum stress times I, and that y would be h over 2. However, my maximum tensile stress cannot equal my maximum compression stress allowed in concrete. As we've said, concrete is much better in compression than in tension. So I will fail in tension long before I fail in compression. So the maximum moment that my cross section can hold, if it's a just pure concrete, no reinforcement, will be limited by my tensile strength of concrete. It'll fail in tension, and compression up at the top is just hanging out like I can do this all day, right? So that's why we have to add in our tensile reinforcement. So, what are the assumptions for flexure in reinforced concrete? This is all about our elastic beam theory a little bit. Plane sections. Remain plane, as in if I have a little beam section subjected to moment, those cross sections will stay straight even if I can't draw them straight. Alright, this right here remains plane. That's what it's talking about. The strain in our reinforcement is going to be equal to the strain in our concrete at the same location. That means the concrete and steel are perfectly bonded. And the stresses in the concrete and reinforcement are going to be calculated or computed from their stress strain data, right? When concrete is subjected to strain or stress, it follows its own curve, and the reinforcement follows its own curve. The strains are going to be the same, but the stresses are going to be different because they're different materials, right? So let's look at what those stress strain curves look like. If you all remember, steel is this lovely material, right? If this is my, let's see, stress strain curve, steel is this lovely material that we're going to assume is elastic, perfectly plastic. So elastic, perfectly plastic. And on the other side, elastic, perfectly plastic. We're assuming that positive is compression right now. Negative is tension. We're going to assume it's elastic, perfectly plastic, which means it's elastic until it hits its yield point, right? It has this E. Same thing, negative. That's its elastic modulus until it hits this yield stress corresponding to a yield strain. And then once it hits that yield stress, it won't increase. You can apply as much strain as you want and the stress is not going to increase, which means it has yielded and is just, holding its own there. Concrete, on the other hand, has this great curve in compression and this teeny tiny little bit in tension. On the tension side, right here's the compression and tension. On the tension side, we have this value FR, which is our modulus of rupture, or the stress at which cracking occurs because of the tensile stress. And that's got some strain value associated with it. And then on the tensile side, this peak, on the compression side, this peak is our F prime C. which is the compressive strength of the concrete, and its associated strain is called E naught. That is the strain associated with the compressive strength, and E naught, or strain naught, E naught, is about equal to 0.002 for normal weight. Concrete. So our steel is lovely. It looks the same whether it's in compression or tension. Concrete, on the other hand, is a bit of a mess and is not so good in tension, but is great in compression. So here we have a singly reinforced concrete section, assuming it's subjected to positive bending. Singly reinforced because we only have reinforcement on one side. We're only going to look at one side of reinforcement. It's on the tension side, which is the bottom, for positive bending. And we're going to look at the strain versus the stress. First, I'm going to apply small strain until I crack the bottom. Right? If I am in positive bending, my bottom of my beam is in tension. And as I apply more and more strain, more and more load, I will reach the cracking strain associated with cracking of the beam in tension at the bottom. So I'm just going to apply a little bit. I'm going to say cracking on the tensile side. All right, because concrete's terrible in tension. Luckily, I have the reinforcement to pick up the slack. If I draw the associated stress profile with that, it looks kind of like that. This value right here is my modulus of rupture. Right, this value would be the strain associated with rupture. But there's also some steel down here. picking up the stress. That means if I apply more strain, right? I'm going to apply more strain. That's my strain profile. Eventually, I'm going to have cracking. More cracking in tensile side of my concrete. It's gonna start at the bottom. Actually, it's actually down here, right? Is where it starts. Right, it's gonna start cracking down here, and eventually it's gonna start cracking all the way up until the neutral axis, because this whole bottom's in tension. So, more cracking starting from the bottom. Once it cracks, I'm going to lose tensile strength. As I'm increasing my strain, I'm going to lose tensile strength in concrete. So there can't be any stress in my concrete. So if I look at my stress profile, let's say it's cracked until about there, right? If it reaches strain there, associated with rupture, that's my stress. There's no stress below where it started cracking because it has no strength. Once it reaches cracking, it loses all strength. So I'm decreasing how much tensile strength I have in my concrete, but I have my steel. Right. This is saying I have all of this compressive stress. Concrete. I have a little bit of tensile stress in concrete. But I need my steel to pick it up once my concrete loses strength. Well, the blue and red and black make me think of Cat in the Hat. So keeping those stress profiles in mind, I'm going to look at two different points. My cracking moment, that is my moment associated with cracking of the concrete. All right. On the tensile side. If I go back to, here it is, stress the moment equals stress times I over Y. My cracking moment will be my stress, which is my modulus of rupture, times my gross cross-sectional area, over YT, which is the distance to the extreme tensile fiber. My modulus of rupture, I can calculate that according to ACI. This is based off of a lot of empirical data, not empirical, experimental. Ow. Let's see, 19.2.3.1. My modulus of rupture, 19.2.3.1 for my modulus of rupture is 7.5 lambda square root f prime c. 19.2.3.1, page 356. It says lambda according to 19.2.4, which is a correction factor for lightweight concrete. If it's normal weight concrete, lambda is 1, so that doesn't matter. Just reduces your modulus of rupture if you have lightweight concrete. You can read that. It's just on the next page, 357. Right. Lambda equals 1.0 for normal weight concrete. And remember, F prime C is in PSI, and your modulus of rupture is in PSI. That PSI under the square root comes out PSI. It's magical. Your IG, gross cross section moment of inertia, and YT distance from your neutral axis to the extreme tensile fibers, which would be H over 2 for a nice rectangular section. Something to keep in mind your applied moment is greater than your cracking moment, what happens? Your beam cracks. If that tensile reinforcement wasn't there to pick up the slack of that cracked concrete, you would have a brittle failure. Without your tensile reinforcement AS. That is why we reinforce our concrete. If not, concrete would just keep breaking and we wouldn't use it. So that was our moment associated with cracking of our beam. Now, since we have the tensile reinforcement to pick up the slack, our yield point is when the stress in our tension reinforcement yields. It says AS. AS is equal to the yield strength of the steel. If we go back here, we are going to look at the section, the second part, and say apply more strain until reach Fy and in our tensile steel. So let's say we've reached Fy. I can say that the stress in the steel, I'll refer to it as Fs. And now it's going to be Fy. Fs is the stress in the steel. Fy means it has reached the yield stress. We're going to ignore any tensile stress in concrete because it doesn't do us any good. And we're going to call the compressive stress in the concrete Fc. So let's see. Fc is our compressive stress in our concrete. And Fs is our tensile stress in our steel, our tensile reinforcement steel AS. If our section is under reinforced, then that means there's not enough steel compared to the strength of the concrete. Then the steel will yield first. If our section is over reinforced, that means compared to the concrete, there's too much steel. When they're both subjected to similar stresses, then the concrete will fail first. In compression, and we don't want that to happen, right? Think about it. If the steel yields first, that's a tensile failure. It'll happen slowly. If the concrete fails first, it'll be in compression. And it'll be cracking, and it'll be brittle, and it might be sudden. So as a result, our goal is to remain under reinforced so that our steel is our primary source of failure. Because it'll be ductile. It'll be a ductile failure versus a brittle failure, right? You always want ductile over brittle. So with that, I will stop right there. And next we will talk about what this all looks like in the code.